Good morning. The title of my talk today is Deploying Data Analytics to Where the Data Is. I'm going to show you how we work with very complex data, both in the cloud and at the edge. So first, I'd like to start with a motivational slide. This slide actually came from one of our customers. And what they told us is that on the surface, their problem is to maintain operational efficiency, making sure that all of their equipment are working with the highest efficiency without any downtime. But really below the surface, a big problem is improving the performance of their personnel. This is because no matter how good your analytic solutions are, if you cannot get your people to use it effectively, then those solutions are not very good. So helping customers to use their data, use the analytics is a very important mission for us. And once you can monitor all the physical operations and physical equipment, obviously now you can also help to predict supply chain needs. So this is sort of a big problem we solve in the industry. And from this point on, we would like to focus on the technical solution side. So at the very high level, what we do is something called data insight integration. That is, we extract insights from multiple data streams and integrate them together to give customers visibility and an understanding of their physical systems and processes so they can continue to improve them. Obviously, today, customers are producing a huge amount of data in many different locations. Some of the data have been migrated to the cloud, but a lot of the data is still remaining at the edge, on the drilling sites, in the refineries. So in order to get all the insights, we would have to be able to access all of those data and integrate the insights together. And that is what we do at Prescient. So just give a very simple data insight integration example. Let's say that you have an AI solution that uses vibration sensors attached to the surface of a mud pump, say to the front end, hole number 1 here. And the vibration sensor, and coupled with a AI analytics side, tells you that there is a potential problem. Unfortunately, most of this analytics and AI solutions, they don't tell you why there's a problem, because AI is about pattern matching. So it really doesn't know the physical mechanisms behind, the result. So what we can do is we can actually look into the work logbook to figure out when the components were replaced, when they were serviced, are there any potential issues with the components because they were not properly maintained. Then we can look into the EDR data and figure out the total amount of time each component was operating, and therefore tell you if certain components were operating over the typical number of hours, or if they were under stressful conditions for many hours. And finally, we can present all that information to drillers, to operators. We can recommend actions to take, which components they should check. And we can even measure their actions to continue to improve the solution. So this is something that we do by integrating different insights from different data streams. And it relies a lot on integrating domain knowledge into the workflow, but we find this to be very effective, and it really helps AI solutions in supplementing additional information. So then what is the challenge here? The challenge here is that there is simply too much data being collected, and getting the insights out of that data is very, very difficult. And also, most of today's solutions take a long time to get the data ready and then extract insights. So those are the challenges of the industry And those are the challenges we solve in our solution. So at a very high level, what we build is something called a data engine. What a data engine is combines data pipeline, which is about getting the data and transform the data, validate it, produce high quality data. But in addition to the data pipeline, we also add data fusion, that is combining different data streams together to make it more meaningful. Data analytics, that is using either physics models or AI models to figure out what are the meaningful events inside the data streams. And finally, we put all the data on a event data layer, so that's easily usable by other applications like BI or AI or any other type of data applications. So one of the unique things we can do in our solution is we can basically drag and drop these data engines to run in different locations. So for example, some of them can run in the cloud, some of them can run at the edge. They are horizontally and vertically scalable. What that means is that we can drop multiple containers to process data streams coming from a source. If there are many, many data streams, if the operations are complex, then you would need to horizontally scale the data engines to handle that. Vertically scaling means that you can increase the size of your machines to do the data processing. So by doing this, we are able to collect and work with data, whether the data is located in the cloud or at the edge. And another interesting thing is that we don't certainly provide all the analytic solutions here. For example, our solutions often take outputs of existing AI solutions and analytic solutions and integrate them with other data sources to give more meaningful results. So we typically work with AI solution providers in the predictive maintenance, in the anomaly detection space. And very often we also work with machine vision solution providers because the output of machine vision are essentially insights that we can integrate with other data insights. So this is a more specific diagram to show what's inside a data engine. We've already mentioned that it includes data pipeline, data fusion, data analytics, and event generation. So the raw, messy data and structured data comes in from the left. By the time it comes out to the right, it's basically structured, meaningful events that can be easily analyzed by BI software or used by AI engines or used in other applications. So this is an example of an event generation. Let's say the data that comes in is pressure data from the EDR, and the pressure data could come in every second, right? Very fast amount of data. And so what our data engine does is, it looks at this data and it says, oh, I can see when the pump got turned on and when it got turned off, right? That's very easily to do. By looking at this picture, we know when that happens. But then it can also apply analytics to the pressure waveform to figure out whether it's operating normally, or there's warnings, or there's alarms, and it can tell you what the different warning or alarm codes are. So then that would be pressure events that can be combined later to form additional insights. So one of the things immediately you notice is that the pressure data, there's just a lot of data, right? Coming in every second. And very often, in addition to pressure data, there are many other type of data that comes in. But there's not a lot of events that happens, right? So by converting raw data into events, you can reduce the amount of data volume by a factor of 10,000 or more. So that really simplifies the way that to work with huge amount of data. So this is what the picture to the bottom lower right illustrates. The input into our data engine can be huge number of data streams with huge amount of data, but what come out are events that happen far less frequently, and therefore there's not a lot of demand on the processing of putting those events together. In other words, the first set of data engines on the left, what they do is event generation, and the data engine on the right does event fusion. So by doing it this way, we can process huge amount of data through our system. So now let's look at an event generation example. This one actually shows two different types of events. So first, let's look at the liner event. The liner event is basically keeps track of when the liner in a mud pump gets replaced. And the liner event typically comes from the work logbook. So let's say the work logbook is stored in some database or data warehouse. We have a logbook connector that constantly monitors what is the logbook data. And whenever a liner change happens, we generate a liner event that tells you that, oh, the liner change happened with the size of the new liner. That's a liner event. So this information by itself is pretty useful because, BI down the line can look at liner changes across time to understand what's the frequency of change, what are the different liner sizes drillers are using, etc. But here's something very interesting. The liner event is actually related to the pressure event. So we already saw that we have pressure data coming from the EDR. So we have an EDR connector that monitors pressure data in pretty much real time. And whenever we see an event in the pressure, for example, the pump turn on, we can start to build a pressure event. But the warnings and alarms for the pressure depends on the liner size. Different liner size would give different warning and alarm thresholds to the pressure. So now what you need is a function in the middle that computes the warning and alarm thresholds that would need to go into the pressure event. And this threshold, whenever a liner event happens, this function looks into a stress table that gets the corresponding warning and alarm, and then feed that into the pressure event block. And so the pressure event block can generate the correct events. So this is a sort of a more complex event because it's dependent on another event. And with liner events, pressure events, and other events, you can combine them further to give you additional insights. So things can get pretty complicated pretty quickly. In addition, almost always, the initial raw data has issues, right? They may have missing values, null values, bad values, and we see that all the time. So you have to handle that situation. And then the logbook, connector could be getting data from the cloud. The EDR data connector could be getting data directly on the drilling site. The pressure event could be computed directly on the drilling site, but it requires some data, threshold data that comes from the cloud. So as you can see, even something relatively simple becomes complicated in implementation. And that's what our software does. It reduces a lot of the complication. It automatically checks for data validation. You can basically drag and drop, build this event generation as shown here in graphical form. And this really simplifies data insight integration significantly. So this is what the software looks like. It's a functional block programming type of software. You can drag and drop blocks in here, and each block contains basically data engine that can run anywhere the block is associated to. Association means that you can associate this block with hardware or virtual machines anywhere they are located. Once you do that association, whatever data engine you build in this software would be deployed to run in their associated hardware or virtual machines. So this is really a distributed data engine builder software. And you can build many different data engines running in different locations and combine the outputs of them, fuse them together in the cloud or at the edge. So it gives you that freedom to build pretty complex data solutions. And you can deploy machine learning models in this blocks. You can update them remotely across many different locations. So really gives you that flexibility to build fairly sophisticated data solutions in one single canvas, basically. So this is an example block. So it's an EDR block. It's associated with a particular edge device running locally, maybe on a drilling rig. And if you double click on the block and go inside, this is the data flow. So for example, first, this block tells you to sample the EDR data periodically. And this one sets up your credentials to access the EDR. This one is a data connector that gets the data from the EDR. And this is a data engine that processes the data, analyzes the data, extract events, and etc. And those are basically debugging nodes that can plot or print data that comes out of the data engine to the screen. So it makes it very easy for you to build solutions. And if we double click on the EDR data engine block, it opens that up, and this is what's inside. So there's a data validation block. In fact, this data validation is pretty much automatic. You can also specify your own validation rules by writing a JSON data structure. So you don't have to write code. You just need to define your validation rules in JSON. And then, once the data is validated, you're extracting pressure events, you're extracting pump hours events. So the data engine allows you to convert from raw data to events. To me, it's actually very important for the solution to be able to be in a hierarchical structure. This is because once you want to do pretty complex data engine type of operations, you simply cannot do it flat, on one canvas, because then it becomes unmanageable. Having this hierarchical structure allow you to manage that complexity. And once your data operation becomes complex, most of your time is not spent on building your data algorithms. Most of the time is spent on managing that complexity. So having this visual, modular, hierarchical type of design technique, it's very easy for you to manage that complexity versus, say, you build this solution in scripting. And as you can also see, this solution is self-documenting, right? So anybody from engineer to the manager to different teams, they can look at this and sort of understand, what are the different components of the solution. So this is very useful for collaboration among different teams. This is another example. It's a machine vision example. It just turns out you can build machine vision in the same solution, which is pretty cool. So for example, this is an Intel i7 device that's running remotely. And you can deploy a machine vision model to the Intel device. And then you can maybe test it by sending an image to it and get that inference out, right? So the inference results are basically your events. So this is really neat because you can combine the machine vision solution with your data analytics, with your data engine. You can deploy your machine vision solutions to many, many different sites. So the platform is quite flexible to handle different type of applications on it. So ultimately, what are we trying to do here, right? What we're trying to do is that our customers have many different type of data. They're located in many different locations. So the data engine would allow them to be able to clean the data, produce high quality data, extract events from it, and finally generate this event data layer that can be consumed by different type of applications, BI, AI, digital twin, ERP, and other type of applications. So the event data layer contains high quality data. It contains events, right? Which is is a useful information from the raw data. So this allows you to basically manage your messy data, and allows you to make your data much more useful and usable. So what example here I'm going to show is a operational digital twin solution. A operational digital twin solution essentially takes in real-time data and gives you real-time visibility, alarms, warnings, instructions. But it also does historic data analysis so that you can understand over long term how your machines and physical processes are operating. How do you improve the efficiency? How do you improve the performance of your personnel, etc.? So the way that we build operational digital twin is using the distributed data engine technology to build all the data flows and to extract all the events. And then the events can be fed into a visualization software. In our case, we typically use Grafana, but obviously you can use Power BI or Tableau, and any other type of a BI or visualization software. And when we build visualization using Grafana, for example, we can deploy the visualization in the cloud, but we can also deploy this to a particular site or many sites. So that makes it very flexible. In a typical digital twin solution, even complex ones takes us 4 weeks to 8 weeks, which is significantly faster if you were to build it using software. Which probably takes anywhere between 6 months to 18 months. And it's very easy to update your data engine data flow, very easy to update your visualization because all of them are low code. So this makes it very fast for customers to iterate, to continue to improve solutions. We really think this is a huge advantage for customers. So this gives you a overview of what we do, what our data engine does, and what our low code philosophy is, right, for building everything from the data all the way up to the visualization. Happy to answer any questions, and happy to chat after the talk. Thank you.